Okay, so now in the lecture 2, I'm sure that I'm too much ambitious of this, so I will skip some part. So we discussed this very nice Abrikosov vortex lattice in large superconductors with this six-fold shaped cores. And the question we asked ourselves for many years was what happens when the size of superconductor itself is comparable to the size of the superconducting core. And several works were done on this, specifically on lead grown on silicon in ultra-high vacuum, and you can get very nice atomically flat nanocrystals of lead, and these crystals are connected to the external world via so-called wetting layer, a single monolayer of lead, which is in this case is not superconducting, it's just metallic, it's conducting but not superconducting. It is amorphous wetting layer of lead. So what you see here is blue, is atomic terraces of silicon with atomic steps covered by single monolayer of lead, amorphous character. Okay, and here you have faceted 1-1-1 oriented lead crystals. Okay, so how we do it, I will skip, it's quite easy. So this is a collection of such islands. The thickness of these islands is 7 monolayers. Its magic thickness, I skip Y. But what is important that we have these islands, and if you do tunneling spectroscopy, you see that all these islands are superconducting, as shows this gap map. So we measure the conductivity at 0 bias. And if there is a gap, the conductivity is low, and this is 0. Black point is 0, so it's fully gapped. You also see that the wetting layer is not gapped, so it is normal. So I don't lie. Now you apply a magnetic field, and yeah, and this size, the size of this island, you see this 200 nanometers. So this is about 300-400, and etc. So what you see is that now I apply a field of 60 millitesla perpendicular to the islands, and I clearly see Abrikosov vortex cores to appear. Okay? The first question to student is, why do the vortex core appear here and not here, for instance? Why do they appear in this island, not in this? Sorry? We have defects, right? This is one position, but this guy also has defect, but no vortex in. This also has an effect, no vortex in. What is true that you understood very well that the defects will tell where the vortex will sit. Okay, but why, for instance, this guy has already one vortex and not this one? This has, this not. This has even two of them. Okay, the answer is here. It's in kinetic energy of currents. So if you have a disk, superconducting disk, with a magnetic field perpendicular to the disk, imagine that the disk is so small that no diamagnetic response is possible. Then the vector potential in London gauge is simply 1/2 vectorial product of external field times R, where R is a distance from the center. And by Ginzburg-Landau, the Meissner currents will flow due to this vector potential, which is just proportional to B and proportional to the radius vector. It means that the current will flow like this, as shown here. They will be 0 here and linearly rise towards the border. The kinetic energy is proportional to the square of currents. Okay? And the total energy, you should integrate over R over dr up to the radius of your sample. And then immediately you see that the kinetic energy of current of these islands is proportional to B square, but this is just the square of currents, times diameter in power 4. Because you have more place for Meissner current to circulate, and they are bigger and they are border. That's why here, in this island, for instance, you get much more kinetic energy of Cooper pairs than in this one in the same field. Okay? That's why the vortex core, setting a vortex, becomes energetically favorable, because of course you will lose a condensation energy in the vortex core, but you will win because with the vortex core will come the vortex currents that circulate in the direction opposite to the Meissner currents. And the total kinetic energy will drop down. And so when the balance, the sum of the energy of the vortex core plus total kinetic energy is less than kinetic energy of Meissner currents, then you get a vortex phase. And of course it happens first in largest islands. Okay? Now let's go to the higher field. So we have more vortices. They already start to organize in a lattice, you see, like in a Abrikosov case. But of course they respect the boundary conditions, because in the boundary condition tells us the current cannot flow across, the supercurrent cannot cross the boundary. Okay, so we have a very interesting case here near the boundary. We will always have on the very edge, it will always Meissner current which will dominate, and inside it will be vortex current that will dominate. So we will have some region in between, very close to the edge, where no current will circulate. In this region, the superconductivity survives. You see, the gap exists here, and even where here, at higher field, we completely suppress the superconductivity inside the island. The color is the same outside and inside. You still have the superconductivity in the border where the current perfectly compensate each other. And this regime is called HC3 regime. So HC2 is when the distance between Abrikosov vortices becomes comparable to Xi. But you can go further, you can still have surface superconductivity, and this is clearly the case. It's called HC3 case. Okay, so now one effect I would like to show you is that if you get a sample as small as few coherence lengths only, and if the shape of the sample is rounded, then putting two vortices nearby will not be the energetically favorable situation. And look on this sample in the magnetic field. So here it starts to have one vortex, here it still have one vortex, and here it has two vortices, and here it has three vortices. So here again you have one vortex, two vortices, three vortices, and we know that they are one or two or three because we observe transitions between different situations which are topological transition. You have vorticity 0 in the Meissner phase, then you have a vorticity 1 in this case, vorticity 2 in this case, and vorticity 3 in this case. But you have only one object, you have no two separated objects. Moreover, the way the wave function decays from here is linear, parabolic or hyperbolic depending on the vorticity, and this is a signature of so-called giant vortices, which are forbidden in type 2 superconductors in macroscopic, but which could be stabilized due to the boundary condition. Okay? So, I would like to say one thing, that this situation where two islands appear close to each other made us think about producing a lateral Josephson junction. Because here we have a superconductor, here we have a superconductor, and here we have a normal metal, so it should be probably create a link. So if you go outside a single island and you measure nearby, you will observe that the superconducting gap doesn't disappear abruptly, but rather follows some evolution. So this red line is what you measure on the island. The next line, red line, is what you measure once you are on the wetting layer as close as possible to the island. And then when you go away from the island, you get a reduction of this proximity effect. And this is a theoretical consideration by Usadel theory. So in a diffusive wetting layer, which is disordered amorphous layer, we have a so-called dirty limit proximity effect, where superconducting correlations, not superconducting gap, there is no superconducting gap in the proximity effect, there is no superconductivity, there are no Cooper pairs, there are only Andreev quasi-particles, okay? For instance, here you see that immediately you go from here to here, okay? Just here to here, no gap anymore. And theoretically, it's just one point in which you get a zero conductance. You have always excitations outside the superconductor. Okay? So, now if you put two superconductors close each other, and then you can measure a so-called mini gap. When they are close each other, then Andreev quasi-particles can go back and forth, what Leandro told us a few hours ago. And if you look on this from the top and you do the spectroscopy over a line linking the two islands, then you can see that there is a hard gap, superconducting gap on both sides. This is the gap of lead, and you have a mini gap inside the link. Okay?
Why is your lead TC suppressed on your island?
Sorry?
You showed the lead TC of 6.2, which is a full degree below the normal TC. Why is it suppressed?
Because the thickness of these islands is only 7 monolayers.
So it's not bulk yet?
It's not bulk. Okay. It's not it's fully open gap, but the width is not, isn't it? Actually, we cannot know actual temperature. We just take 2 delta over actual critical temperature. We just measure the gap. And we say it is.
I should not take that seriously.
No. The only measure we do is the gap. Of course, if we go to 6.2 Kelvin, we see that the gap closes. But since we discussed it with Andrei, the temperature, the resolution near TC is quite nothing. Okay, so this is okay. Now.
What about HC2?
HC2 is some in between. It's about 300 millitesla.
Is lead a type 1 superconductor?
Lead is type 1, of course.
Why are we talking HC2?
Yes. Yes. Lead is okay. Good question. Bulk lead is type 1 superconductor. So it means that lambda is smaller than psi. So in principle, the vortices cannot appear there. But in these islands, we have a very specific case in which the top side of the island is atomically flat surface. But the bottom interface is dirty. In which sense? In sense that we have an atomic lattice of lead sitting on atomic lattice of silicon. Okay? And there is a mismatch in between. So any electron going to this interface gets scattered, because it is rough, okay? So, what is the mean-free path of this island? Typically, the mean-free path of electrons in this island is 2 times the height. 2 times the height, okay? In such a case, you apply Ginzburg-Landau formulas for dirty superconductors, and immediately psi becomes smaller and lambda becomes bigger. And you have a proof of this validity because you measure the width of the vortex core, which is exactly 2 times psi, and you observe that the psi here is at least 2 times smaller than the psi you expect in bulk lead. Okay? So, now, let us look what happens in between. Okay? In between, indeed, you see that we have some superconducting correlations, some depleted mini gap that appears here, there, and not here because it's too far. Okay? And there it is strong, there it is strong. And now I do a zoom here, and you see that there are very nice correlations. I see the gap everywhere as proved by this blue color that shows me that there is a mini gap. Now, if I apply a magnetic field, of course, you already saw this picture. I see the vortex here, there, 2 there, and there. But I also see something strange appearing here. Okay? So this link that was quite homogeneous everywhere starts to be destroyed in the middle. Okay? Now, let us take a look on what happens here. There are 3 links, G2, G3, G4. And now, if we apply higher magnetic field, we break this link, again, even here, and these two appear here. It is broken a little bit. What is nice that when we go to yet higher fields, in these locations when the link was destroyed, it reappears back. So this all looks like interference pattern. And it is Josephson physics, and we can understand it very easily. So when you apply a magnetic field, in each islands you have Masonry currents circulating. All Masonry currents in all islands circulate in same direction. Here counterclockwise, and here counterclockwise, if this is a spacing between two islands. Okay, so the currents circulate there, and these currents, they produce a phase shift which is in this direction, in this island, and in that direction, opposite direction in that island. And when you look on the shifts in between islands, you can decide what is the Josephson current that flows through these parts. If here you have plus pi and here plus pi, no Josephson current circulates. The same for the phase shift 0 to pi. Okay? But now you start from here, you accumulate a shift plus pi, you accumulate no shift here, and you accumulate shift 2 pi there, no shift there. So over this area, you accumulated a 2 pi shift as around a single Abrikosov vortex core, okay? Except that here we are in the normal material. There is no Abrikosov vortex there. So, but there is a Josephson vortex possible. So you have a singularity of phase, okay? But here there is no order parameter. The superconducting order parameter is 0. There are only Andreev quasiparticles. They form this, okay? And of course, it's possible to simulate this. I don't discuss this, but with no free parameters, we are able to simulate vortices in exact positions in islands using Ginzburg-Landau, and beyond islands using effective Josephson model. Okay. I want to present you. Okay, it's still okay. I want to present you some effects which were recently studied. When I say recently, last 10 years, related to the size of size effect of superconductors, not necessarily lateral, as we discussed it with vortices, but it could be a thickness, okay, on the scale of electronic wavelengths, not on the scale of Xi, but on electronic wavelengths. For instance, one of the first experiment was done already in 2006, in which people create Eom et al. They created sort of thick films of 5, 6, 7 monolayers of lead. So you see this is 180 nanometer scale bar. Xi is about 30 nanometers, so laterally they are quite big. But this film has a flat top, but it sits on 3 different terraces, down-going terraces of silicon. Okay? So it is thickness, here is 5 monolayers, here it is, in this terrace is 6 monolayers, and this is 7 monolayers. So you see how it works. Okay? And so what they measured that the superconducting gap was oscillating depending on the number of monolayers of such different ions. And that was linked to the fact that in the vertical direction, you confine your electronic K Fermi, your electronic waves, you confine like in a quantum well, okay? And you have some magic thicknesses for which one of the confined levels sits on the Fermi level. In such a case, you enhance very strongly the density of states. With the density of states, you enhance TC, you enhance the gap if you go with the BCS. And these oscillations are due to the fact that for some thicknesses, the peak of the confined state sits on the Fermi level, and for others, it's away from the Fermi level. But later on, unfortunately, for this paper, it was a very precise paper by Brun et al. In EPFL, in which they studied different different thicknesses, and they just found a continuous decrease of the superconducting gap as a function of reduced thickness. So if with reducing thickness Tc is reduced, how it can go toward yet smaller thicknesses? So in this paper, it was done down to 6 monolayers because the layers, thinner layers, are very difficult to produce. They are often unstable because the underlying surface starts to interact strongly with the layer, and then you cannot produce what you want. Okay? Just God can tell you what He allows. What is nice of lead on silicon is that surface science people already discovered that you can grow a single monolayers, not only amorphous as we did, but you can also produce crystalline films of single monolayers. And depending on annealing conditions, so how do you do? Of course, you start with amorphous layer. You put your atoms on the surface and you get amorphous. And then you anneal to some temperature. And the atoms rearrange each other. Depending on initial condition, how many atoms of lead you put at the beginning, and what is the annealing temperature, you can get different reconstructions. Okay? And all of them are quasi-stable. Why they are quasi-stable? Because of mismatch of bulky BCC lead and silicon. So you can obtain an infinite number of reconstructions of different density, different order. And in 2010, Zhang et al. Showed that some of them, for instance, so-called striped incommensurate lead, or square root 7 by square root 3 lead, okay? Square root 7 by square root 3, it appeals to the size of this unit cell, okay? And these two materials, they observed a superconducting gap inside of this. So it's one layer of lead, one atomic layer of lead, okay? And it looks superconducting. And this gap closes at 1.8 Kelvin for the striped incommensurate lead, and it closes at 1.5 for square root 7 by square root 3 lead. So is it possible this such a monolayer to be superconducting? The answer can be done only either by measuring a current and proving that there is a Josephson current, or by proving other characteristics of coherent condensate, as for instance vortices. Because if you have vortices, it means that you have a phase. It's coherent. So that's what we did. We repeated this experiment of Zhang. We also observed the gap, okay, in both materials. And we also observed the vortices. So in SiC, the vortices exist. And they are very nicely abricos-like with rounded with normal state, normal cores. And in square root 7 by square root 3, the situation is a little bit more difficult. The atomic steps play a role of Josephson junctions, and they first trap Josephson abricosov vortices on atomic step, and when only at higher magnetic field, well, when all abricosov Josephson vortices are saturate atomic steps, you get other vortices inside terraces as here. Okay? And you see that they are not rounded as in abricosov case, they are much more distorted, and this physics is related to disorder features. Okay? So similar results were obtained by our Japanese colleague who worked on a similar system, square root 7 by square root 3 of indium, the same material, the same structure on silicon, and they observed exactly the same situation, elongated vortices and atomic steps at low field, and more rounded than in our case, abricosov vortices, pearl abricosov vortices on terraces. And we explained it both. We explained it by so-called abricosov Josephson vortex predicted by Alex Gurevich in '93. So now I would like to, so one monolayer of lead is superconducting, okay? But somehow I can say probably it is not surprising, because one monolayer of lead is still two-dimensional material, and in two-dimensional material, the density of the spectrum energy as a function of K is continuous. If it is continuous, then you can open a gap, superconducting gap. But is it possible to quench superconductivity by reducing all directions? And this is what we did recently. So in a material, a bulky material, the mean interlevel spacing in the conductance band is related to K Fermi and the size of the material. It's something you can get very easily considering the limited size. Okay, and in 1959, Anderson suggested that when the interlevel spacing becomes comparable to the delta, to the superconducting gap of the material stops to be superconducting. The idea, the straightforward idea is as following. In a superconductor, an energy, characteristic energy per pair is 2 times delta. Per electron is 2 times, per electron is delta, okay? So, basically, if you don't have electrons enough within the range of delta to create pairs, you cannot get superconductivity, you cannot get condensate. And there were several experiments trying to prove or disapprove this. And we got to this result by accident, but I would like to share with you this result. So, we deposited lead on indium arsenide, 110 direction. In this surface, 110, indium arsenide has a two-dimensional electron gas in the surface. And our idea was to get ballistic proximity effect between lead islands and this indium arsenide. That would be nice, to get Andreev bound states and etc. Unfortunately, there is almost no coupling, electric coupling between those islands and this two-dimensional gas, by 2 reasons. One is that below lead, this two-dimensional gas depletes, so it gets away. And another reason is a very strong mismatch of K Fermi, of wave vectors, between a semiconductor and a metal. So simply, our electrons from lead, they cannot go in because there are no places at this K value. So finally, our islands sitting on indium arsenide, the most important coupling is just capacitive coupling. That's what we found. And then you have a so-called Coulomb blockade junction, in which you have external electrode, a ground, the tip is grounded, the sample is biased. In between you have your island, and they are coupled by tunneling resistances and tunneling capacitors. In such a case, you expect 2 features, characteristic features, to appear on tunneling conductance spectrum. You don't see the superconducting gap here immediately, because the superconducting gap is completely screened by Coulombic energy, okay, which is larger. You see the Coulombic gap, and you see strong peaks, and these peaks are so-called Coulomb star Ks. It comes from the fact that depending on bias that you apply, here you apply more and more bias, you put electrons of higher and higher energy, and at some moment, 1 electron can sit inside the island. 1 electron sits inside the island, it blocks coming of other electrons. So you need to tilt more to allow second electron to sit. Of course, other electrons, they go in, go out, but in total, they sit 1, 2, 3, or 4, etc. electrons. Okay? Each time you have a peak, each time the number of electrons changes, you have this huge peak. Okay, this is just standard case of so-called Coulomb star case. It's just Coulombic energy. It's classical case. You consider just electrons as classical particles of charge E. Okay, what is nice with a superconductor, that if this island is superconducting, adding one electron to a superconductor costs a charging energy plus or minus the gap energy. Why? Because, as told us Andrei Varlamov, that in superconductor all electrons are bound in pair. So imagine you have a even number of electrons, so you have some number of all electrons are in pair. Now you want to put an extra electron, so you will pay a charging energy plus the fact that there is no extra electron to bind in pair. Now,